Hello students, in our previous class we learned about cubic polynomial and the relationship between the zeros and the coefficients, like coefficients of x cube, coefficient of x squared, coefficient of x and the constant term. Okay, in this class we will learn how we can solve a cubic polynomial problem. Okay, so here we choose these three problems. In this first problem, we have a polynomial, that is f of x equals to x cube minus 5x squared minus 16x plus 80, and we have a relationship between its zeros, and the relationship is that its two roots are equal in magnitude but opposite in sign. Okay, so with the help of this condition we have to find the zeros of this polynomial. So let us study how we can find the zeros of this polynomial. Solution 1. Given polynomial is f of x equals to x cube minus 5x squared minus 16x plus 80. Comparing the given polynomial with f of x equals to ax cube plus bx squared plus cx plus d, we get a equals to 1, b equals to minus 5, c equals to minus 16 and d equals to 80. Since f of x equals to x cube minus 5x squared minus 16x plus 80 can be written as 1 into x cube plus into minus 5 into x squared plus into minus 16 into x plus 80. Okay. So comparing the given polynomial with the general form of cubic polynomial, that is ax cube plus bx square plus cx plus d, we get a equals to 1, b equals to minus 5, c equals to minus 16 and d equals to 80. Okay. Now we have to let the zeros of this polynomial. Let alpha, beta, gamma be the zeros of the given polynomial such that polynomial where alpha equals to minus beta. By the problem. So here we choose three zeros of this cubic polynomial as alpha, beta, gamma, where alpha equals to minus beta, because it is given that its two zeros are equal in magnitude but opposite in sign. So here we choose alpha is equals to minus beta. Okay. So this imply alpha plus beta equals to 0. Now we have to apply the relationship between the zeros of a cubic polynomial and the coefficients of its cubic term, quadratic term, linear term and constant. In our previous class, we learned how these relations are coming. Okay. So now we have to use this relationship. So therefore, alpha plus beta plus gamma is equals to minus b by a, imply alpha plus beta plus gamma equals to b. B means minus 5 and a means 1. So these imply alpha plus beta means 0 from this condition. 0 plus gamma is equals to 5. So this will give gamma equals to 5. Alpha into beta into gamma, that is product of the zeros, equals to minus d by a. This implies alpha into beta into gamma. Gamma means 5 is equals to minus of d. D means 80 by 1, because a equals to 1. So this will give alpha into beta equals to minus 80 by 5. Cancelling 80 and 5, we get alpha into beta equals to minus 16. Okay. Here we choose these two relationship, because these two relationship help us to find the zeros of this polynomial. Okay. We can use this relationship also, but without using this relation, we can easily find the all the zeros of this cubic polynomial. Since alpha minus beta whole square is equals to alpha plus beta whole square minus 4 alpha beta, as since p minus q whole square is equals to p plus q whole square minus 4pq. This is an algebraic identity. Already we know this identity. So by using this identity, we get alpha minus beta whole square is equals to alpha plus beta whole square minus 4 alpha beta. So this implies alpha minus beta whole square equals to alpha plus beta means 0. 0 square minus 4 into alpha into beta means minus 16. So this will give alpha minus beta whole square equals to 64. So alpha minus beta is equals to plus minus 8, because plus 8 whole square is 64 and minus 8 whole square is also 64. Okay, that is why alpha minus beta becomes plus minus 8. Case 1. When alpha plus beta equals to 0 and alpha minus beta equals to 8, then solving these two, that means if we add these two equations, then we get 2 alpha equals to 8. by adding. That means if we add these two equations, then we will get 2 alpha equals to 8, because plus beta and minus beta will cancel out. That is why we will get alpha plus alpha as 2 alpha and 0 plus 8 as 8. Okay. So this will give alpha equals to 8 by 2. That is alpha equals to 4. So when alpha becomes 4, so therefore alpha plus beta equals to 0 imply beta equals to minus alpha, imply beta equals to minus 4. Okay. So in case 1 we choose alpha plus beta, alpha minus beta as plus 8. So then by solving these two equations, that is alpha plus beta equals to 0 and alpha minus beta equals to 8, we get alpha equals to 4 and beta equals to minus 4. Okay. Case 2. When alpha plus beta equals to 0 and alpha minus beta equals to minus 8, then now if we add these two equations, that is alpha plus beta equals to 0 and alpha minus beta equals to 0, then we get 2 alpha equals to minus 8 by adding. So this will give alpha equals to minus 4. So therefore alpha plus beta equals to 0 imply imply beta equals to minus alpha. So this imply beta equals to minus of minus 4, that is beta equals to plus 4. Okay. So in these two cases we get when alpha equals to 4, beta becomes minus 4, and when alpha equals to minus 4, beta becomes plus 4. So we can conclude that two zeros of these polynomials are plus 4 and minus 4. Okay. So the zeros, so therefore all the zeros of the given polynomial are 4 minus 4, 5 or minus 4, 4, 5. Okay. So this is the way by which we can find the zeros of this given cubic polynomial. Okay. So in problem 2, we have a cubic polynomial, that is f of x equals to x cube minus 5x square minus 2x plus 24. And in this problem also we have a relationship between the zeros of this cubic polynomial. What is that relation? The relation is that the product of its two zeros is 12. Okay. In the first problem, there is also a relationship between the zeros of this cubic polynomial, and here in this problem also we have a relationship between this polynomial. Okay. So let us study how we can find the zeros of this cubic polynomial by using the relation given condition or relationship between the zeros. Okay. So as previous, solution 2, given cubic polynomial is f of x equals to x cube minus 5x square minus 2x plus 24. Comparing the given polynomial with the general form of cubic polynomial f of x equals to ax cube plus bx squared plus cx plus d, we get a equals to 1, b equals to minus 5, c equals to minus 2, d equals to 24. Since the given polynomial f of x can be written as 1 into x cube plus into minus 5 into x square plus into minus 2 into x plus 24. Okay. So, comparing the given polynomial this with the general form f of x equals to ax cube plus bx square plus cx plus d, we get a equals to 1, b equals to minus 5, c equals to minus 2 and d equals to 24. Okay. Let the zeros of the given polynomial be alpha, beta and gamma, where it is given that product of its two zeros is 12. So, that is why we choose the product of these two zeros alpha and beta, that is alpha beta is equals to 12, since it is given that the product of its two zeros is 12. Okay. Now, we have to use this relationship in this problem. We will use this relationship between the zeros and the coefficients. So, therefore, alpha plus beta plus gamma equals to minus b by a, imply alpha plus beta plus gamma equals to minus, or b means minus 5, a means 1. So, we get alpha plus beta plus gamma equals to plus 5. This is relation number 1. Alpha into beta into gamma, that is product of the zeros, equals to minus d by a, implying alpha into beta is 12, that is why we can put alpha into beta as 12, then these 12 into gamma minus of d, d means 24 and a means 1. So, this will give 12 gamma equals to minus 24. So, this will give gamma equals to minus 24 by 12, that is gamma equals to minus 2. Okay. Now, from 1 this one. Now from 1 we get alpha plus beta plus into minus 2 equals to 5. This implies alpha plus beta minus 2 equals to 5. This implies alpha plus beta equals to 5 plus 2. This implies alpha plus beta equals to 7. This is relation number 2. Okay. So by the given condition and the relationship between the zeros and the coefficients of cubic term, quadratic term, linear term and constant, we get alpha plus beta equals to 7, gamma equals to minus 2. Okay. Therefore, alpha minus beta whole square is equals to alpha plus beta whole square minus 4 alpha beta. This is an identity since p minus q whole square is equals to p plus q whole square minus 4pq. So by using this identity, we can write alpha minus beta whole square equals to alpha plus beta whole square minus 4 alpha beta. So this imply alpha minus beta whole square equals to alpha plus beta means 7 and alpha into beta means 12. So this will give 49 minus 48. That is 1. That is, sorry, alpha minus beta whole square equals to 1. This implies alpha minus beta equals to plus minus 1, because whole square of plus 1 is 1 and whole square of minus 1 is also 1. That is why we get alpha minus beta whole square equals to 1 as alpha minus beta equals to plus minus 1. Okay. So we get two cases. In case 1, we have alpha plus beta equals to 7 and alpha minus beta equals to minus 1, plus 1. Adding we get, now if we add these two relationship or equations, we get alpha 2 alpha, because beta plus beta and minus beta will cancel out. So alpha plus alpha will give 2 alpha equals to 7 plus 1, 8. So 2 alpha equals to 8, imply alpha equals to 8 by 2, that is alpha equals to 4. So therefore alpha plus beta equals to 7 imply 4 plus beta equals to 7, imply beta equals to 7 minus 4. 7 minus 4 will give 3. Okay. So from case 1 we get alpha equals to 4 and beta equals to 3. In case 2 we have alpha plus beta equals to 7 and alpha minus beta equals to minus 1. Adding we get 2 alpha equals to 7 plus into minus 1. This will give 7 minus 1. 7 minus 1 will give 6. So alpha equals to 6 by 2, that is alpha equals to 3. So therefore alpha plus beta equals to 7 imply 3 plus beta equals to 7, imply beta equals to 7 minus 3, imply beta equals to 4. Okay. So the zeros of the given cubic polynomial are 4, 3 minus 2 or 3, 4 minus 2. Okay. So this is the way by which we can find the zeros of a cubic polynomial when the relationship between its zeros is given. Okay. So in problem 3 we have different condition to find. That is, here we have a special relationship between the zeros. That means we have to show a special relationship between its zeros. Okay. So what is its special? What is the special relationship? The special relationship is that if the zeros of this cubic polynomial are in AP, then what will be the condition? Okay. So before solving this problem, we have to know what do you mean by AP. Okay. So let us know about AP, or let us learn about AP. Arithmetic progression, or in short AP. One, two, three, four, continue. Minus 20, minus 18, minus 16, continue. Okay. So here we choose two different groups of values. They are 1, 2, 3, 4 continuing and minus 20, minus 18, minus 16 continuing. Now if we follow the first group of values, then we will get 2 minus 1 equals to 1, 3 minus 2 equals to 1, 4 minus 3 equals to 1. If we follow this second group of values, then minus 18 minus of minus 20, that is minus 18 plus 20 is equals to 2. Minus 16 minus of minus 18, that is minus 16 plus 18 equals to plus 2. Okay. So if we follow this first group, then we will see that any term 2 minus 1 equals to 1, 3 minus 2 equals to 1, 4 minus 3 equals to 1. That is, any term minus its previous term always gives a fixed value. In the second example or second group of values, minus 18 minus of minus 20, that is minus 18 plus 20 will give 2. Minus 16 minus of minus 18, that is minus 16 plus 18 will give 2. Okay. That is, in this group of values also, any term minus its previous term always gives a fixed value. Okay. So if a group of value progressed in such a way that any term minus its previous term always gives a fixed value, then that progression is known as an arithmetic progression. Okay. So here the here into groups of values, we observe that any term minus its previous term always gives a fixed value. Okay, so the progression where the above process are followed is known as an AP. Okay, that means if a group of value progressed in such a way that any term minus its previous term always gives a fixed value, then that progression is known as an arithmetic progression. Okay, that is why we conclude that the progression where the above process means any term minus its previous term. Always gives a fixed value, then that progression is known as an AP. Okay. If three numbers are in AP, then we can let them as L minus M, L and L plus M. Okay. So if three numbers are in AP, then we can let them as L minus M, L and L plus M. Okay. So these three numbers will form an AP because L minus of L minus M, because any term means this is the second term, any term minus its previous term, that is the second term minus this first term will give L minus L plus M, that is M, cancelling L and minus L, L plus M minus L, that is third term minus its previous term, that is third term minus second term will give L plus M minus L, cancelling L we get M. Okay, so in these two cases, that is second term minus first term we get M and third term minus second term we get M. That is why we can conclude these three numbers, that is L minus M, L and L plus M are in AP. Okay, so to solve this problem, we have to know this part about AP. Okay, so this is not our arithmetic progression class. So when we will study about arithmetic progression, then we will properly learn what is the actual meaning of arithmetic progression. Okay, so this is the short note about arithmetic progression, because this short note is very much important for us to solve this problem number 3. Okay, so in problem number 3 we have to find the condition between the zeros of this cubic polynomial f of x equals to x cube minus px square plus qx minus r if its zeros are in AP. So given cubic polynomial is f of x equals to x cube minus px square plus qx minus r. Comparing the given polynomial with the general form f of x equals to ax cube plus bx square plus cx plus d, we get a equals to 1, b equals to minus p, c equals to q, and d equals to minus r. Since f of x equals to 1 into x cube plus into minus p into x square plus q into x plus into minus. Okay. So comparing the given polynomial this with the general form ax cube plus bx square plus cx plus d, we get a equals to 1, b equals to minus p, c equals to plus q, and d equals to minus r. Okay. Let since the zeros of the given polynomial are in AP, let the zeros be L minus m, L, and L plus m. Okay. So therefore, alpha equals to L minus m, beta equals to L, and gamma equals to L plus m. Okay. So since the zeros are in AP, so we can let them as L minus m, L, and L plus m. Okay. So we can represent alpha as L minus m, beta as L, and gamma as L plus m. Okay. Now alpha plus beta plus gamma equals to minus b by a imply L minus m plus L plus L plus m equals to minus of b. B means minus p by a means 1. We can easily cancel this plus m minus m. So this will give 3L equals to p. This will give L equals to p by 3. Okay. So thus we find the value of L. Here L is also one of the root of this cubic polynomial. So therefore we can say beta equals to L equals to p by 3. Okay. So since beta is a root or zeros. Beta is a zero of the given cubic polynomial, therefore f of beta equals to 0, because every zero of a polynomial satisfy that polynomial. Okay, so since beta is a zero of this cubic polynomial, then if we put beta in place of x, we will get f beta, and that f beta will be equals to 0. F beta equals to 0 imply f of p by 3 equals to 0, imply p by 3 whole cube minus p into p by 3 whole square plus q into p by 3 minus r equals to 0. So this will give p cube by 27 minus p into p square by 9 plus p cube by 3 minus r equals to 0. This will give p cube by 27 minus p cube by 9 plus p cube by 3 minus r equals to 0. After finding the LCM of 27, 9, 3 and 1, because nothing is here means 1 is the denominator of a minus r. So the LCM of this is 27. So this will give p cube minus 3p square plus 9p cube minus 27, sorry, this equals to 0, minus 27r equals to 0. This will give minus 2p cube plus 9p cube minus 27r equals to 0, because 0 into 27 is equals to 0. So this will give, after simplifying, 2p cube equals to 9p cube minus 27r. So this is the required condition. So therefore 2p cube equals to 9p cube minus 27r is the required condition. Okay, so this is the way by which we can find the condition when the zeros of a cubic polynomial are in AP. Okay.